First of all, welcome back to week number 3 of MATH113 section 1. Today is day number 5 into the semester, and I would like to walk you through some of the very interesting things today, including that you will have to get some papers ready so that you're going to do some practice in class. Now remember, we're doing calculus now, and the theme of this is to make sure you understand the applications of this mathematics in today's world, okay? And so I've just got some very interesting video, which I hope that towards the end of today's class, you will bring back home an extra piece of applications of calculus in our daily living. Okay, to begin with, normally your teacher will ask you these questions, and I will do it every week. If you go to week number 3, all right, today I do not have a microphone. Someone has used up all the batteries, and I'm now charging them. So I have to yell a little bit with my voice. Okay, week number 3, when you go to the topic online discussion forum of this week, you see that I have posed 2 important questions here. Let me enlarge it first. The first one is, what have you learned from the second week of the semester? Okay, we are at the beginning of the third week. What have you learned from the second week of the semester? And I would like you to do something on your own. Talk to the partner next to you. And in particular, what I'm expecting you is that you should have watched the following tutorial videos at home. If not, I'm going to give you one today. Alright, so, but actually not one, more than one, but let me just try to give it to you one at a time. Okay, the second questions that I would like you to answer. Okay, again, at the beginning of the week number 3. When you go to week number 3 abroad, when you come down to week number 3's 2, to track your learning, when you come to the public online discussion forum for week number 3, the second question is, what are the things not so clear at this point to your understanding in this course? I assumed you should have gone through the syllabus, you should have gone through the websites, including the first 2 weeks' blogs. If you have anything you want to ask me, you can ask me directly from this particular forum by clicking on the reply button and type in some of the questions you have. If you do not want your fellow student to read the questions, you can directly send your questions into Dr. Buck's Q&A hotline for this week, which is just below the topic online discussions forum link. Okay? So the 2 questions very important at the beginning of each class, and I hope each one of you should get online so that you can start typing in some responses. And in the meantime, my job here is to steer your review of the work. So may I invite each one of you, when you get to this classroom, get ready your mobile devices, get online to the Moodle environment, because you always have something to type in. Okay? Could you do that? Make sure you're already online to the Moodle environment of this course. Okay. You will take your time. You can do anything with your mobile devices, including hopefully 90% of the time when you use your mobile devices when you are in this classroom, you're referring to what I'm telling you to go online to this Moodle environment. Because I know that some other teachers do not like to use this text devices in class, but you know it's different in this class. You need to use them, all right? So remember, last week, before we introduced to you David Jervison's first lecture on calculus, we bring you to this particular slide. Let me enlarge it a little bit. Okay, this is a slide where you have a preview into some of the important calculus lessons that you should get yourself familiar with. Okay, last week we start with calculus functions. All right, we have a discussions that one of the implied usage of calculus today, after you watch that particular video, 8 minutes, for what calculus is used for, we come to the consensus that calculus is one important tool for us to do mathematical modeling. Okay? for us to do mathematical modeling, and we can use it in order to understand something complicated. So if there is something really complicated, and if we have to build a model to study it, it's going to be very expensive. So instead of building a physical model, we build a mathematical model to simulate the operations of that something. And so we say calculus is a very good candidate for us to use to build mathematical model. And then we come to the discussion step. When we use calculus to build mathematical model, we need to start out with something much more fundamental. And we say that something, it's a function, because it's like a machine, which when it takes in something, we can see that as input, it's going to produce something, we can see that as the output. And what is inside the machine is what we call the designs of the specific modeling features, all right? And so we introduce to you 10 specific characteristics of what a function is, okay? Or what functions are all about. And we brought in the beautiful lady from Calculus Expert. She spent about 10 minutes time helping you to understand the most basic things about functions. Today, we're going to bring her back again several times, particularly speaking in the context of equation modeling, all right? So you know what a function is, you know what an equation is. So, but to begin with, I want you to get ready. Now that you should know something about functions, okay? I would like you to understand one important way to express a function. Okay, so get ready for about 6 minutes review of what are some of the important ways to distinguish if one given figure represents functions or not. And that is what we call a vertical line test. All right? So, a first review.
Versus an equation. Remember that an equation is just any expression with an equal sign. So for example, if we said y equals x, that would be an equation because it has an equal sign in it. A function is always an equation. We're always going to have an equal sign in a function. But a function is a special type of equation. And for that reason, oftentimes, instead of using y, we use the notation f of x to say that f is a function of x to indicate that this is a special type of equation called a function. Now, a function is an equation such that there's only one output value of y for every input value of x, which basically just means if we were to graph the function and we choose any value of x, it's only possible to get back one unique result for y. In order for an equation to be a function, that has to be true for every single value of x within the domain of the function, for every single value of x that we can pick. So for example, if I look at this first graph here, let's say that I pick this value of x right here. Maybe it's x equals 1, x equals 2, whatever. It doesn't matter, but I'm picking this value of x. If I look at the graph here, there's only this one single value of y that's returned when I plug in this value of x. So if this were an equation, if I plug in this value of x, and again, let's say maybe it's x equals 1. If I put x equals 1 into this equation and I evaluate the equation, the value I get back for y is this value right here, which is maybe 2. So I plug in 1 for x, I get back 2 for y, and there's only one result for y. On the other hand though, if I pick this value of x right here, maybe let's say this is negative 1, and I plug it into my equation, I can get back 2 possibilities for y. I can get back this value for y, and I can also get back this value for y, because I'm plugging in this same x value. If I draw a vertical line here, I'm plugging in the same x value, but there's 2 y values that can be returned to me as a result of plugging in that x value. Since there are 2 possible output values for the single input value of x, this graph does not represent a function. Even though this relationship right here is 1-to-1, I plug in one x value, I get one y value, as long as I can find any single x value that could possibly return to me 2 different y values, then I know the graph is not a function. Which brings us to the vertical line test. Basically, all I'm doing right here is I'm testing different values of x, right? I can pick all these different values of x, and I can look at the graph, and I can see which y values are returned to me. You know, this y value is going to get returned to me when I plug in these different values of x. If I ever find a point for x that returns to me two different values for y, then I know that the graph does not represent a function. And basically what this is saying is that if I can draw any perfectly vertical line that intersects the graph at more than one point, so I can draw this perfectly vertical line, and I can see that it crosses the graph at 2 points, 1 point here and 1 point here, that means that for this single x value right here, I can get back two different output values for y. So this graph does not pass the vertical line test, and therefore the graph is not a function. In other words, a graph must pass the vertical line test in order for it to be a function. So if I look at this graph right here, I can draw a perfectly vertical line right here, and I can see that it only intersects the graph at this single point, so I know I'm okay there. If I draw a perfectly vertical line here, I can see that it only intersects the graph at this single point, and I can do that for lots of different vertical lines. But if I draw a perfectly vertical line right here, I can see that it intersects the graph at 2 points. This point right here, which is off of the graph, and this point right here. So because of this other point right here, this graph does not represent a function because it does not pass the vertical line test. It doesn't matter if I can draw a million vertical lines that only intersect the graph at one point. If I can draw one single vertical line anywhere that intersects the graph at more than 1 point, the graph does not pass the vertical line test and therefore is not a function. So here's what I would want to say. I'm going to go ahead and say not a function here, and this is also not a function. What about my third graph right here? If I try to draw vertical lines, and again I can draw them anywhere I want to pick, but if I draw vertical lines here, maybe here, I can see that each vertical line that I draw is only going to intersect the graph at one single point. There's no vertical line I could draw on this graph that would intersect it at more than 1 point. Therefore, this graph passes the vertical line test, and I can say that this graph represents a function. If I look at my last graph here, I can see that I have a circle, and right away I can tell that I'm going to be able to draw a bunch of vertical lines that intersect the graph at more than 1 point. So I have this line here, I have this line here, I can draw it closer to the edge of the circle, and I still intersect the circle at 2 points. So what this tells me is that this graph does not represent a function, and in fact, I can conclude from this that a circle is never a function because I'm always going to be able to draw a vertical line that'll intersect it at more than 1 point. So a circle is never going to be a function, and this graph certainly does not represent a function. So that's how you use the vertical line test to say whether or not a graph represents a function.
Okay, you've learned something now. Now let's do something with a piece of paper.
In this video,
we'll get to that in a minute. Now, I would like you to learn how to apply what you've just learned in this video into your daily living, called applications of the mathematics you just pick up in your daily living. It's very simple. Now, each one of you, if you have a piece of paper, A4 size, you can cut it into 4 small pieces of equal size, okay? Because you have 4 persons in your table. We do not need to use a large piece of paper. So I did not bring my piece of paper, so maybe you need to share, okay? You have a large piece of paper, A4 size, cut it into 4 pieces, something like this, okay? And pass a small piece to each one of you in the table. And I want you to do a very quick applications of mathematics, okay? Thank you very much. You're very generous. Next time I'll bring some extra paper for you. I'm in a rush today, so I think it's like today. Okay, make sure each one of you on your table have a small piece of paper, all right? Yes, if you have paper, share, because we want to make the best use of resources. It's a very quick actions of math, okay? Are you ready? If you have a small piece of paper, each one of you get a pencil or pen ready, okay? It's your job. You cannot tell anybody to help you, but it's your job. Alright, so what you need to do with that small piece of paper in about 2 minutes time, you're doing you're going to do some quick thinking. Quick thinking. I want you to draw a graph on a plane. Okay, in a plane you have x-axis horizontally, you have y-axis vertically. So you draw one horizontal axis, you draw one vertical axis. So principally speaking, you're going to have four areas: the positive, positive, the positive, negative, the negative, positive, and the negative, negative. Okay, everybody understand this basic concept, right? So you draw this cross, okay, representing a plane with both a horizontal axis and a vertical axis. Now the next thing you need to do is you need to draw a graph on that plane. A graph on that plane, okay? Now whatever graph you're going to draw very much depends on your thinking. You are going to use the graph to represent something of your own, okay? Say if I'm going to use a graph to represent my blood pressure from beginning in the morning 8 o'clock to now, which is about 3 o'clock in the afternoon. Suppose this is my blood pressure. So are you going to put your blood pressures into the negative regions? Does it make sense? Are you going to put your blood pressures graph in the negative, positive area? That you have to decide which quadrant of that is which of the four areas, okay? Positive, positive, negative, positive, positive, negative, negative, negative. Which area of the cross are you going to use to represent your graph? And you also need to label what your graph represents. If it represents my blood pressures from 8 o'clock this morning to 3 o'clock in the afternoon, which quadrant should I use? Okay? Now if I'm going to represent my weight from day 31st last month to day number 8 this month, which particular area I'm going to use? It's really up to you. Use the graph to represent something physical or something, well, it could be abstract. For example, someone will draw a graph to represent the index of his emotions. Up means happy, low means sad, in between means stable, whatever it is, okay? So you think about something you want to represent with your graph, and you have to design which area in the graph are you going to put it. If you're going to put it in negative, negative, what does it mean? You're going to interpret. And then you are going to tell it what function are you going to use to represent these particular entity that you put it on the graph, okay? It's a 2 to 5 minutes exercise. 2 to 5 minutes exercise. Now remember, what is not a function? Can that pass through the vertical line test? Or is it a composition of functions that you learned from last class? Okay? Think about this. You can represent this. Yes. Thank you very much. We've got leaders coming up. We've got coordinators. Yes. You can explain it to the rest of the table if they do not understand what they're going to do. Represent something on your graph. Okay? Make sure you understand what the graph represents. And then tell what function it is. Okay? What function it is. Or is it a function? I do not want you to just use the techniques of math. I want you to use the thinking of maths, okay?
I got back the microphone. Yes, I got back the microphone. That's very good. You don't need to yell. Thank you. You're going to draw a graph. Each one of you is going to draw a graph. At least each table produces one drawing. The graph is going to represent a physical entity or whatever entity it represents. And you have to decide on which specific area. We have 4 possible areas to put the graph. And after you have drawn the graph, you have to tell what functions represent the graph. Okay? And it's in the functions. What kind of test can you use to determine if the graph represents a function? Okay? They give you 2 more minutes. It can be anything, right? So use mathematics to represent something. We're going to tell you you're going to use a sketch, the graph. Okay? Any volunteer? Table volunteer to tell us what your graph is all about? Let me set up the visualizing. So we are ready. So once your graph is ready, you're going to show your graph and explain it to the whole class, okay? You have your graph ready? Are you willing to share? To tell something of the meaning of the graph? Okay, it's fine. It's fine. All right. So just put your piece of paper here. All right. And then it's this here. So then you can give this microphone. So over there. You can see that. Yes. Let's say you go soup here. We need some focus. Okay, we got it. So are you ready? Help us to understand what it means. Excuse me, let's listen. Okay? Can you introduce yourself? Your name is? Yes, firstly, could you just hold the microphone? Yes, thank you.
It presents my for math test mark in has moved
Okay.
the final time.
Final exams, okay.
This is my first year.
Okay.
Second year.
Okay, first is,
Third year.
oh, that's, it makes sense, it makes sense.
Year.
Okay. So the x-axis represents the year, right? Year 1, year 2, year 3, year 4, something like this, right? Okay, fine. So the vertical axis represents a score, right?
Yeah.
A score, okay. Thank you. So, is it a function? Can you tell it? It could be generated by a function and represent a function, right? Can you tell if it represents a function?
Yeah.
Because?
Each one x
Yes, one vertical line test could only hit one point, right, in the graph. That's good. Thank you very much. We thank you very much for Christy sharing with us a simple graph representing the score he obtained while in high school, year 1, year 2, year 3, year 4. So let's see, do you have any volunteer in this table? Volunteer? Are you ready? Are you ready to share? Get you? Yes, come in. Yes, it's your time. Thank you. Yes, we can see that. It's okay. That's the way it is. There we go. Introduce yourself.
Hello, my name is Cynthia.
Cynthia.
And the XSS represents the date.
The date. Yes. Of the week. So
No, and
number of days.
yes.
Okay.
No. It's in this month.
Okay. The days in this month. Okay.
And the Y-SS represents the money I spent.
The money you spent.
Yeah.
Wow, you spent a lot of money on day 7.
On the first day, I just spent a little because I didn't have lunch outside.
Alright.
And on the third day, and it's the holiday, and I stay at my home, so I didn't spend.
Okay, we understand that.
And on this day and yesterday, yes, because I have to have lunch with my friends, so
So
I have
it's
to
expensive
spend
lunch.
more than 100.
You treat your friend for the lunch.
No.
Wow. Individually, you spend almost close to $120 for lunch. It's going to be a very big lunch. Okay. Thank you very much. It's very good. Okay. So, someone from this table, Star, are you waiting for someone else? Okay. Can you come? Yes. Bring your graph. Yes. Come. Yes, come. It's your time to share with us your function. Can you bring it? Because everybody can see it. Put it in the visualizer. You draw. Okay. I do not have here. Yeah. No. Use your piece of paper to draw. Yeah. Your function's over there, right? Because I didn't bring the markers today, so I need to use the visualizer. Yeah. You draw a function on the piece of paper. Can you do that? Any. Have you got it ready? Do you have a pen? No, we don't have it here. Can you get a pen for him? Yes. Just put a piece of paper here, and you can start drawing your graph. Yes. It's okay, on the other side. People can see you. Alright, so can you draw a picture of the functions, the graph of functions, to represent something? Okay, so let me just. Okay, that's good. So tell us something about what this function means. What does it represent? What does it represent? So it represents something, right? You want to use this graph to represent something plus your home. So what does it represent? X represent what? So 1. Okay, thank you, stop. Is that right? Anyone? Yeah, that's okay. Anyone from this table? Yes, please. Is it Doris? Okay, thank you. Yes, I passed you the microphone, okay? You have to hold it up in other words. Okay, very clear.
This graph is about my emotions, and the x-axis represent the time, and the y-axis represent my feelings. When I get up every morning, I'm very upset because getting up is really a bad thing. And breakfast lunch and dinner is my happiest time because eating is really enjoy. And when during the day I'm having classes because I'm getting more and more hungry, so my feelings get down.
Okay.
And that's my graph. And
Okay.
it circulates function.
So yes, it's a function because when you use the vertical 9 test, there's only one point.
Yes.
Yes, thank you. Thank you, Dorothy. Anyone from the other table? Anyone who want to share it with your picture? You want to do it? Yes, from this table? Anyone? You want to do it? Yes, please, thank you. That's what you draw, okay? It's a very clear indication of how we use a graph to represent something, all right? The next question is, how can we get the data there important as a function? I want to hold up your microphone.
My name is Cindy.
Cindy, right?
The X is the date in September.
Okay, that's good.
And the Y is how much energy I have.
Wow, that's good. In terms of what unit?
Huh?
Energy, you can have some kind of unit. You mean
My personal.
personal energy, okay, PE, all right. It's okay.
And the first day I have 20% energy because I need to go to school.
Okay.
And the 1st of September because it is the day off, so I have 100% energy. So that
Okay.
is
I think it's quite interesting. Do you see that today we have a new product called Apple Watch? How many of you got Apple Watch? Oh, thank you. It's a device which could make the best use of the sensors to detect your blood pressure, the amount of oxygens in your blood, and also the breathing rate. Okay, these are 3 essential biological data to help us to monitor patients in the hospital. And also some of the time they can also test the cholesterol level in your body. And I think that is very interesting. Do you have anything to share from this table? Can I give you a chance to tell us what you got? We are just using a simple mathematical tool called a graph, a planar graph, to try in such a way that we could use it to represent something meaningful for us. Hello, thank you. Could I give you the microphone so you can hold it and speak? Just put it here. Yes, everyone can see that.
So my name is Patrick, and I draw this graph as the Y is emotion, your emotion, and the X refers to the difficulty you met in life.
Okay.
So everyone begins born with no difficulty. They met, so after they have studied in primary school, so the problem will met many in the following years. So when you finish the difficulty, you may feel happy. So after that, you also may met some very difficulty for very difficult problems in your coming secondary school life and the future university life. So you may feel sad. So after that, you may try your best to find out some solution.
Okay.
The difficulty. So finally, you may feel so just back to the original emotion or be very happy. So that's
Okay, that's very interesting. You take a long time to tabulate those data. Thank you, Patrick. Okay, we thank you all of you for participating in this simple exercise. And a lot of the time, I think in our school days, we learn a lot of mathematics in terms of the calculations techniques. And we're never given a chance to say, can I use the mathematics in such a way to represent something that means apply it the way we could? Because we're humans, we learn how to use things. So I would like to show you an interesting mathematical application here. Let's see. Oh, wait. I have to make sure the sound is okay, because it looks like because I switch it here, I need to get it back. that I was told that this is the way how to create problem with the sound system. Let's see, let me turn this off. And then I need to make sure that I got back the sound. We should be able to get back the sound. Let's see.
One. Today we're going to talk about how to build an equation that models a story problem we've been given. To complete this problem, we'll first pull out important pieces of information from our story. Then, we'll draw a picture of our problem. And finally, build the equation that models the two. Let's take a look. So, in an equation modeling problem, you're usually given a long, wordy description of the equation that you're supposed to write. And you need to get good at picking out the relevant pieces. In this particular problem, we've been told that a rectangular storage container with an open top has a volume of 10 cubic meters. We've also been told that the length of its base is twice the width of the base. Given that the cost of the material we need to build the base is $10 per square meter, and that the cost of the material we need to build the sides costs $6 per square meter, we've been asked to express the cost of the materials as a function of the width of the base. If you can, the first thing you want to do in an equation modeling problem like this is draw yourself a picture of what you're trying to model. In this case, we have a rectangular storage container with an open top. So we can draw it like this. It's rectangular, and it has an open top, so we won't draw a top on it, and we'll draw our 3D effects here. And now that we have a picture, we want to, if we can, start labeling things on our picture. So we've been told that the length of the base is twice the width of the base. So we can call the width W, and the length then would be 2W because the length is 2 times or twice the width. We don't know anything about the height, so for now, we'll just call the height H. Now we know we're looking for cost, so we want to go ahead and start writing down our equation for cost, which we'll call C. We know that the cost of building this box is going to be dictated by the fact that the cost of the materials for the base is $10 per square meter, and the cost of the materials for the sides is $6 per square meter. So let's go ahead and start with the base. We know that the area of the base is 2W times W, which is 2W squared, and we know that the cost of the materials for the base is 10. So we can say that the cost is 10 times 2W squared, and that takes care of the base. We know that these sides here, the end of the rectangle or the thin side, the area of those will be W times H, right? The width times the height. And there's 2 of them. So we know that we have 2WH for those 2 sides. And we can even describe it as 2 times WH, WH being the area of one of the sides, and of course we have 2 sides. The area of the other 2 sides, these ones here, is described by the length times the height, which is 2WH, and of course we have 2 of those, so we'll say 2 times 2WH. If we add these together, we get the total area for the sides, and we know that we have to multiply that by the cost of the material for the sides, which is 6. So we can add these together because we want total cost, or the sum of the cost. So plus 6 times 2 times WH plus 2 times 2WH. Now we just need to simplify our cost function and make sure that it's in terms of W, because we've been asked to express the cost of the materials as a function of the width of the base, and we know that the width of the base is W. So let's go ahead and simplify our cost function. We see that we get cost equals 20W squared plus, we can say 6 times, here we have 2WH, and here we have 4WH, so we know that we have 6WH when we simplify. And of course, if we distribute the 6, we'll get plus 36WH. So now we've simplified as much as we can, and our cost function is in terms of W, except for the fact that we have this H variable here. So we need to eliminate that in order to say that our cost function is exclusively in terms of W. The way that we're going to do that is by using the only piece of information that we haven't used so far. We used the fact that the box was rectangular to draw a picture, as well as the fact that it had an open top. We used this fact that the base length was twice the base width to label our picture, and we've used our two pieces of cost information. So all we have left here is the piece of information about the volume that we haven't used. We know that the volume of this box is equal to the length times the width times the height. We know that our length is equal to 2w. We know that the width is equal to w, and we know that the height is equal to h. We also know that our volume is equal to 10. So we can set that equal to 10, solve for h, and then plug in what we get to our cost function. So you'll see that we get 2w squared h is equal to 10. We can divide through by 2w squared to get h by itself, and we'll get h equals 10 over 2w squared. Of course, we can divide both numerator and denominator by 2 and simplify to 5 over w squared. This is now what we can plug in for h in our cost function. So we'll see that cost is equal to 20w squared plus 36w times what we got for h, which was 5 over w squared. And because we now have a w in the numerator and denominator of this second term here, we can cancel one of those to see that our cost function is 20w squared plus 36 times 5 is 180. So 180 divided by w, and that's it. There's our cost function in terms of the width of the base, or w.
So I hope you found this video helpful. If you did, like this video down below and subscribe to be notified of future videos.
I would like to make sure that I got back the very last piece, right?
Hi everyone!
36 times 5 is 100w, or w,
Like this video down.
or w.
Okay, let's say we're somewhere here. So do you see a very interesting examples of the applications of mathematics in the context of these solutions? Can you point out where is the relationship? Applying mathematics to solve a specific real-life problem, how much should I pay to buy the material so that I can create this rectangular box without a top? It's a very simple problem. I know every one of you have already done this in high school, but let's try this problem. Do you see where different types of mathematics have been used here to find a possible solution to this question? Any suggestions? Now, there is nothing called right or wrong. Where can you see the applications of, say, calculations of area, arithmetic, geometry, or algebra? And you learned arithmetic, you learned geometry, you learned algebra. Where is geometry used in this? Can't see it. Okay. That's a very good response. Okay, when you study to calculate the area of a particular planar shape, is it arithmetic? Is it algebra? Or is it geometry? When you study geometry, what do you study? Okay, here we are given a rectangular shape. Rectangular shape in the 3D format. Okay? So, is this geometry? Okay? In this rectangular shape, how many sides are there without top? How many? 5. So, I cannot turn this. I really want to make it, you can turn this. 1, 2, 3, 4, 5, right? 5. So 5 sides. If I count for each side, the 2 sides, for each piece there, 5 pieces, you're telling me 5 pieces, right? And for each piece there are 2 sides, okay? So when we are doing these calculations to find the area, when you say 5, are you just calculating the area on the outside or the inside? If we are taking into account the area, there is, if this is a piece of paper, a piece of work, this is one side, this is another side, right? And actually, there are 2 sides of this. Okay? So, when this problem is solved this way, I guess the assumption is we just need material to cover the outsides of the box, not including the inside. Do you understand the first assumptions they make that I'm trying to open up to you? If you have to work out the total amount of material required to cover this rectangular box, both inside and outside, is there any change to the calculations? Okay, now take a look at it. They say, well, for rectangular shape, the cost of the material is per square meter $10 for the base, this base. Okay, but remember the base, the 2 sides, this side and this side. Are they just calculating based on one side or both sides? Does it matter? Okay. If it does not matter, say, okay, per square meter, $10. And for the sides, per square meter, $6. So the sides, 1, 2, 3, 4, $6. So my interpretation is at the very beginning when I'm following the ladies, you're just going to cover the external piece. You're not covering the internal piece, right? Now, what does it mean if I would neither take into the internal pieces? Does it have anything that I need to change here? The cos, it said the base area, it's 2W times W. This is the area. All right? And the side, we have 6 pieces, or we have, say, 2WH. So 2WH is this side. We have 2 sides. Okay, and then WH, we have 2 sides. But where does the 6 come from? The 6 comes from the dollars per square meter. Okay? Logically speaking, it tells you some systematic thinking. But when we look into the systematic thinking here, when we have to ask the questions, when you ask me for the cause of the material by giving me information like this, do I need to care about the questions and ways at the very beginning? This is just for the outside or including the inside? Right? So it is a very interesting question. Now, this is point number 1. The second interesting thing, suppose this is right. Here we got a very interesting piece. Based on this formula, the cos per square meter, then we got the cos. It's an explicit statement, okay, assuming it's right. And finally, after you've done some simplifications, you got the relationships. Relationships between this variable, we call it the independent variable, and this C, we call it dependent variable, because C is going to change as W is going to change. So C is called dependent on W. So if this is an equation that represents a functions, so this is a functions of W. Okay? And W can change. And as W change, C will change. And we say C depends on W. All right, one more thing. W represents the input. C represents the output. And when we talk about the input, we talk about the domain of W, the values W can pick up. That's called a domain. And C represents the range of values that C could pick up. Now the question is it possible for C to be negative?
Yes, but it does not make any sense. But is it possible for these equations to generate a negative c? This is always positive. This, even it's negative, okay? This value is going to be greater than this value. Not very much likely, so c is always positive. So we need to take into account sometime the possible values that the dependent variable is going to take up. And of course, when you go back to here, how to find the domain and range of a function. Please read it at home. Okay? And then to find the values and domain and range from a graph, and then determine if a function is even, odd, or neither. Oh, this is something very interesting. We're not going to have enough time today to do that. No, we should have to do it. Okay, let me do this. How many minutes? Oh,
Hey
4
everyone!
minutes. Okay.
Today we're going to talk about how to determine whether a function is an even function, an odd function, or neither an even nor odd function. To complete this problem, we'll substitute negative x for x, simplify, and then see whether our result is equal to our original function, and even, equal to our original function times -1, and odd, or neither. Let's take a look. In this particular problem, we've been given 3 separate functions and asked to determine whether each one is an even function, an odd function, or neither. To make this determination, in each case, we'll plug in negative x in place of x to our functions, simplify, and then the result will tell us whether the function is even, odd, or neither even or odd. Let's go ahead first and plug in negative x to our first function. We'll get negative x to the 5th plus negative x. And again, we just want to simplify as much as we can here. Negative x to the 5th will give us negative x to the 5th like this, minus x. At first glance, this might not look the same as our original function, f of x, but if we factor out a negative sign, we'll get negative x to the 5th plus x. And we can see that our functions are the same, but for the negative sign out in front. We have in our original function, x to the 5th plus x, and in our simplified function here, x to the 5th plus x. The only difference here is this negative sign. As you can see, since we know that f of x is equal to x to the 5th plus x, we could just as easily substitute f of x for x to the 5th plus x, and you can see that we get negative f of x. That's exactly what we were looking for to determine that this is an odd function, so we know here that we have an odd function. We'll go ahead and do the same thing with our second function. As always, we'll plug in negative x in place of x, and we'll get 1 minus negative x to the 4th. When we simplify this, we'll get 1 minus negative x to the 4th will give us a positive sign. That negative sign inside the parentheses will go away, and we'll just be left with x to the 4th. As you can see really quickly, we're right back where we started at f of x. So this just becomes f of x. And as you know, when we get back to our original function, f of x, we know that that's an even function. We've defined these down below, by the way. We can see that if we get back to f of x, we have an even function. If we get to negative f of x, as we did in the previous problem, we have an odd function. And then when neither of those things is true, we get neither even nor odd. Let's go ahead and look at our third function. Again, as always, we'll plug in negative x for f of x. That's always how, negative x for x. That's always how we make our determination of even, odd, or neither. So we'll see that we get 2 times negative x minus negative x squared. We'll simplify this as much as we can, and we'll get negative 2x minus this negative x squared. That negative sign inside the parentheses will go away, and we'll be left with x squared. As you can see, this isn't equal to f of x. They're exactly the same except for this negative sign out in front of the 2x here. But we didn't get f of x exactly, so we can't call it even. Even if we try to factor out a negative sign and we get negative times 2x plus x squared, we still don't have our original function here because our original function is 2x minus x squared, and we have 2x plus x squared, so we can't call this odd either, which means this is going to be neither. And that's it. That's all there is to it when it comes to determining whether or not your function is.
Now tell me, you can tell, if this particular functions that we investigate here, is it an even function, is it an odd function, and does it matter? I hold you responsible for thinking a little bit further, because there's a typical kind of mathematics that does not consider the whole picture. I told you the reasons why, but normally it looks like fine. Now, with the remaining time, I want to stimulate you a little bit by bringing you back to calculus and what is calculus for this time. And this time we're going to push you through a very interesting episodes of scenario that you're going to save your own life if you know calculus. But I'm going to give you only half of the picture. All right? So keep that in mind. All right, let's come back here. This is a typical application of calculus. And I think you're ready for it.
Okay, looks like the coast is clear. I'm Colin Adams, and I'm making this video to try to help you to survive the zombie apocalypse. With all the, oh, hang on a second. Trouble folks, real sorry. Not gonna have time to do this right now. I'll catch up with you later. Okay, I think we're good. Let's try this again. I'm Colin Adams. I'm here in my office. I'm a math professor at Williams College, or at least what's left of it at this point. And I've been out there. It is bad out there right now. The number of zombies is through the roof. It's growing really fast. The number of humans is dropping really fast. And this idea of numbers changing like that is an idea that comes up in calculus, and it's called the derivative. So the derivative is measuring how fast quantities are changing. In this case, we're interested in how fast the number of humans is changing and how fast the number of zombies is changing. So let's think about what contributes to the number of zombies at any given time. And just for convenience, we're going to think of each zombie corresponding to a red lentil. So the total number of zombies will just be the total number of red lentils, and we're going to call that number Z. What can change that number? Well, first of all, zombies, if they can't find anybody to eat, they will eventually starve to death, and that will decrease the number of zombies that we have. On the other hand, when a zombie interacts with a human, that zombie either gets sustenance by eating the person, or that zombie can convert somebody into a zombie, which will also increase the number of zombies that we have. So now let's talk about the total number of humans. And let's represent each human with a brown lentil. So the total number of humans will be equal to the total number of brown lentils, and we're going to call that number H. Now, unlike zombies, as far as we know, humans can have babies, and that will increase the number of humans. If there's a zombie-human interaction, the zombie can attack a human, kill the human, and therefore the number of humans will drop. Now, if there's a lot of people and a lot of zombies, then there's going to be a whole lot of interaction. That is not going to be pretty. I've seen it. It is awful. For the love of Newton. Things are looking bad out there. Don't know how much time I have. I mean, this situation really reminds me of situations that occur in nature. You know, think about a wolf population and a deer population. The wolves are the predators, the deer are the prey. Very similar to the situation we're in, only the zombies are the predators and we're the prey. So let's think back to when this whole thing started. And there were lots of people and there were just a few zombies. But those zombies had lots of people to convert into zombies, and that meant that the number of zombies went up dramatically. As that was occurring, the number of humans was dropping precipitously. And eventually we got to a state where there were very few humans left and lots of zombies. Now, that couldn't last because, of course, the zombies no longer had people to eat, so the zombies started to starve to death. until we reached a point where both the number of humans and the number of zombies was small. In that situation, the humans had a chance to recover, and the number of humans started to increase again. Now, unfortunately, that meant the zombies again could convert a lot of people into zombies, and suddenly the number of zombies started to increase. And I think that's the situation we're finding ourselves in now. So it looks like this is just going to repeat. The number of zombies will go up, the number of people will go down. The number of people will go up, and the number of zombies will go down. Like an endless cycle going on and on and on, unless we can be smart, and unless we can overcome them using our brains. Now, wonder who that is? Yeah, what's up? What's your
I hope you're responsible for watching the second part of this particular video and see how you use the idea of the derivative that we introduced to you as of last class to help yourself. Remember what we studied last class. Now, please make sure you understand it. We did introductions to derivative last week, and we come to the examples of derivative, but I've used the zombie as an example. Okay, go home, finish reading this. That means watching the video produced by Professor David Jerrison. And then let's come to sections number 3. In the part number 2, Professor is going to introduce to you the rate of change of productions of zombies and productions of humans. Okay? So I hope that with this much motivation, I can encourage you to go home to study that. And when we come back on this Friday, I will help you to understand this much better. Limits and continuity. Okay? Let me take attendance first. We do not have a lot of zombies outside. Okay? We just have humans. Take a little bit about the examples we've gone through today. It's very interesting. Alright? Wiki, thank you. Johnson, thank you. Alex, thank you. Stella, thank you. Viviana, thank you. Jordan, thank you. Star, thank you. Chaos, thank you. One you, thank you. Louise, thank you. And then it's David. David, thank you. Shen Chun, thank you. Viola, thank you. And then Candy, thank you. Mei Ling, thank you. And then Iris, thank you. Bella, thank you. Cindy, thank you. Vivian, thank you. Patrick, thank you. Jeanette, thank you. Ivy, thank you. Celia, thank you. Michelle, thank you. And then Nizzy, thank you. All right, so the next page. Here we go. Doris, thank you. Calvin, thank you. And then Jeremy, thank you. Andy, it's okay. Thank you very much for your coming back. So I'll see you again on Friday. Let's get ready. All right, watch the video and get ready. You will have another kind of exercise this Friday about the derivative. Okay. It's better for you to make a piece of paper this time. One piece of paper will be good. All right. Thank you very much. That's it for today's MATH 113, section 7. I'll do this Friday. Stay tuned.